So today we are going to talk about linear regression. Now, this is a very, very fun topic for me because I perform linear regression almost on a daily basis. For you, I think it shouldn't be an entirely new topic because you've probably done linear regression. Even if you haven't done the actual math behind it, I'm pretty sure at some point in your careers, you've taken some data, plotted it in Excel, and fit a line into that data. So you have done linear regression before, I'm assuming. Today, I'd like to talk a little bit about the math and the general philosophy behind linear regression and regression analysis in general. So first off, I guess before we even start talking about the mechanics and the general things, I'd like to answer the question of why do we need regression analysis, right? So not all physical relationships can be quantified analytically. We already talked about this at the beginning of the semester, right? Sometimes there are some physical relationships that we can't really quantify analytically because we don't have access or ability to record all the relevant data or theory. So in these cases, we are going to have to determine our relationships empirically. And when I say empirically, what I mean is we're going to make those determinations based on measurements. So when we talk about analytical methods, you have the theory, and from the theory, you get results. When we talk about empirical methods, you start by collecting results, and from those results, you develop the theory. So empirically is kind of like an analytical method in reverse. So what does that mean? Well, to determine an empirical relationship, we are going to have to record data and then use that data to formulate an equation. Of course, here we need to be careful because you know that since we're going to come up with some relationship from data, we need to be very, very careful with the amount of data that we capture or collect. Sometimes two different properties, it could be physical properties, it could be chemical properties, it could be any type of property. Sometimes two different properties are deterministic. A deterministic property is essentially, or a deterministic relationship is essentially telling us that properties have a clear relationship that can be modeled perfectly. One example of a deterministic relationship is the average velocity of a moving object. The average velocity of a moving object is measured as the change in the object's position with respect to the time it took to make that change. If the object is moving at constant velocity, then this equation gives me the true or the actual velocity of the object. That's a deterministic relationship. Pretty easy relationship to find, right? We want to find the velocity of a car, we can measure the length and time, okay? Sometimes we will be dealing with relationships that are not deterministic. In other words, sometimes we can't really fit in a nice, beautiful equation such as this one in order to come up with a relationship. Sometimes the equation doesn't exist. As an example of a non-deterministic relationship, we can think of the following. We can think of the power consumption of a house. So W dot is work rate, which is power. The power consumption of a house related to the size of the house. So assuming that you want to estimate, how much power will be consumed in a typical neighborhood, a general neighborhood, and you don't have any information about that neighborhood other than an aerial map, then perhaps you could try to see if there's some relationship between the power that will be consumed by each house and the size of the house. That's a non-deterministic relationship because there is no equation, there is no relationship that actually guarantees that there will be some sort of correlation here. We need to consider that factors such as consumption habits, household size, weather will all affect our power consumption. So we can't really come up with a deterministic relationship based only on this variable, which is the size of the house. We could try to come up with other deterministic relationships, such adding more. such as, again, consumption habits, perhaps the number of electronics in their house, the number of outlets, the number of rooms, all those different things can be considered. However, if we only want to consider something such as the size of the house, we will have to turn to statistical methods to come up with that relationship. In this class, we are going to use a method called regression or regression analysis in order to determine non-deterministic relationships and maybe even try to come up with a model for these non-deterministic relationships. Now, there are many different forms of regression analysis. For this class, we're going to focus on linear regression, which is one of the simplest forms of regression analysis and a very powerful one as well. You will be surprised at how applicable linear regression can be for a lot of different fields. So let's start by looking at the data in table 11.1 of your textbook. I actually have the textbook right here. And if you don't have the textbook with you, these data from the table were posted on the content section. You go to content modules 14 and 15. You are going to see a spreadsheet called table 11.1, and you can see the data that we are going to show today. On your textbook, I have it on page 282. What we have here is a plot of hydrocarbon levels versus oxygen purity. And what we have here is a plot of that data. We have it graphically shown. I want to focus on the actual scatter plot, the XY plot. What we have here are dot diagrams, but we don't need to worry about those just yet. Okay, so we have our data here in the table, and we have our plot here. Now, we already mentioned that descriptive statistics, right, the idea of presenting data, allows us to draw conclusions visually without even having to look at the numbers. So let's not focus too much on the table. Let's just look at the graph. And just by looking at the graph, what can you tell me about the covariance of these two variables? Is it positive covariance, negative covariance, or is there no covariance? Yeah, on the chat, it looks like we have positive covariance. That's correct. So we do have positive covariance. What positive covariance means is that as one variable increases, the other one should increase as well. What if my measurements had only considered this range? Maybe this range. What will we conclude about the covariance of the data? We would conclude that it's negative. So, of course, it's important to have a representative sample in order to identify this positive trend. Okay? Now, Jaden in the chat mentioned something interesting. Jaden says that it looks linear. Okay. That's a really interesting observation, that it looks linear. I don't particularly see that it is linear, but I'm going to take your word for it. Okay? So taking your word for it that this relationship, the relationship between the two variables looks linear, then we could probably plot those two variables with a linear equation. So thinking that this relationship kind of looks linear, then perhaps our data should follow a linear equation. Now, of course, looking at the graph itself, you can see that it clearly doesn't follow a linear regression. I mean, the data points go up and down, but perhaps while an individual data point or two individual data points may not follow a linear relationship, perhaps the mean of those points does follow a linear relationship. So if I take the mean, the average value of my dependent variable y with respect to the independent variable x, then we can say that that mean will follow a linear trend. And that's kind of what we are seeing here. And I'm assuming that that's what Jaden saw as well when he looked at the graph, right? Even though between these 3 points, we don't have a linear relationship, perhaps if we take groups of points and calculate the means of those groups of points, then that mean will look almost linear. So that's what we're going to do. We're going to say that the mean of my data set follows a linear relationship. And what does that linear relationship look like? Well, just like any linear equation, we have an intercept and a slope. In this case, I use the variable beta naught for my intercept, and I use the variable beta 1 for my slope. These two variables are collectively called regression coefficients. So we assume that the mean of this data set will follow, right, a linear relationship. However, if we look at the graph, we can see that it doesn't actually, the individual values don't actually follow a linear relationship. So then how can we move around that? Well, let me just plot a graph. It's not going to be exact. Let's say something like this. Perhaps we can see from this graph that, or we can assume from this graph that they will follow a linear relationship. So what that means is that if I were to take groups of these points and calculate their means, my assumption tell me that that will look like this, like a straight line. That's my assumption. Now the real points, the actual points are actually not on the mean. In fact, and from this example, none of my points are on the mean. What this means is that there will be some difference, some deviation between our assumed mean and the actual observed or recorded points. This deviation can be expressed in the form of an equation. We can say that my points y will be equal to the mean of those points with respect to the independent variable plus some sort of deviation. So this measurement between the point and the mean, I'm just going to call it my deviation. Of course, this allows us to come up with a nice equation for my point y. That equation will be the mean, which we can see is a linear equation, plus the deviation for each point. Now, this equation itself may not be linear because this deviation changes as you move through your points. However, at least part of this equation, a component of this equation, is linear. This is an example of an empirical equation. It's an equation that we are trying to come up with based only on observing data, not on any actual theory of the data itself. Now, using this equation, we could try first to approximate that mean. In other words, if we can figure out what the value for what the intercepts for this mean are, then we could try to approximate them here through some sort of approximation or regression method, which we'll learn in today's class. And then we could try to estimate the dispersion from the standard deviation. Remember that the standard deviation is a measure of the spread or dispersion of a value. So if we know the standard deviation, we could use it to more or less guess or estimate the actual dispersion. What this will result in is a value of y that may be closer to the real values, even though they may not be exactly at the real values. So what I would like to talk about now is then how we can find this estimation of the mean, how we can find these regression coefficients. Now, the procedure for finding regression coefficients, it's actually very straightforward. Equation here, an equation there, and as long as we follow all the steps correctly, we will be able to estimate what those regression coefficients can be. Now, I want to make something clear here. We will never really truly know what the regression coefficients are. Instead, we can estimate them. We will never really truly know because the equation for the mean is the mean for the population. However, we're only dealing with a sample. So even though we'll never truly know the regression coefficients, we will at least be able to estimate these coefficients. So if you return back to the figure in your textbook 11.1, you can understand that perhaps drawing a line would be the best fit to the data. But now the question is, which line is the best fit to the data, right? I can draw a line however I want. I can select the slope. I can select an intercept. But the reality is that there should be at least one line, right, that we can consider to be the best fit. And how do we find that? We're going to borrow from Carl Gauss's book, where he proposed that the best fit is the one that minimizes the sum of squares of the deviation. And that kind of makes sense, right? You want a line that has as little deviation from the mean as possible, or as little deviation from the values as possible. This method that Carl Gauss proposed is called the method of least squares. And that's what we're going to use to try to estimate these regression coefficients. So what is the method of least squares? It's a method that allows us to minimize the sum of squares of my deviation. And again, why do we need to consider the square of the deviation? Because we obviously want those values to always be positive so that they can add up. So let's see the analysis. We have our graph with our data points. And then we have some mean. We don't really know what this mean is, but that is what we're trying to find. So what can we say about this graph? Remember, this is y, this is x. So what can we say about this graph? First off, each point has some deviation from the mean, some vertical deviation, right? What that means is that if I select a random point here, I'll just call this point yi, then that point should be equal to the mean, which is the point corresponding to this line. I'll call it mu I, so mu at this position, plus some deviation corresponding to that position. Right? So far I think we can agree. Of course, I can rearrange this equation to say that my deviation is going to be the actual point minus the mean, right? Now, Gauss's method of least squares, the word least is important, says that the square of this deviation has to be minimized. So if I take the sum of squares of that deviation, I'll call it L, which is the sum of the square of the deviation. That should be the same as the sum of each point in our observation y minus the corresponding point for the mean of that observation squared. We can agree with that, right? We have the deviation being equal to the observation minus the mean, and the method of least squares means that we want this L value to be as small as possible. So the sum of these squares of the deviations needs to be as small as possible. Now we've already defined earlier in today's class that the mean, assuming that it's a linear equation, then that mean should be calculated, right, as a linear equation. In other words, we can write it down as follows, right? So we have our value for the sum of squares, y minus some intercept coefficient minus some slope coefficient minus the corresponding x observation for that value. So how do we find beta naught and beta 1? We want to find the smallest value of this variable, the smallest possible value of L. Math whizzes and math geniuses, if I want to find the smallest or the largest value of anything, what's a strategy that you probably got from your calculus class or pre-calculus class? What's a strategy that we can use? We could integrate. Is there perhaps a better way to find the smallest or the largest value? Because integration just gives me a sum of all the values, but I'm not really trying to add anything, right? Christian says we can derive, right? We can derive to find the maximum and the minimum values, and that's absolutely right. Remember, our derivatives represent the change. And if you take any graph, and then you have the derivative at the highest point and at the lowest point. What is that derivative equal to? Derivative at the highest point or derivative at the lowest point? What are they equal to? 0, correct. There's no change. The tangent line is horizontal. That means that the derivative at the highest or lowest point is 0. Assuming, right, that our graph doesn't have multiple maxima and minima, then we could try to find the smallest value of L. There is no largest value of L. If you just think conceptually, you can modify this line as much as you want. You can keep modifying it such that L can grow up to infinity, right? So there is no largest value of L, but there should be a smallest value of L. So think of starting the line completely vertical, right, where L is infinity. You can start modifying it and perhaps moving it around as L becomes smaller and smaller. Finally, when you get to the actual smallest value, if you keep moving on, then your L will start to increase. So we can conclude that there is a smallest value of L, and that L goes from infinity down to 0 and then up to infinity, or the derivative of L will go up to infinity. All right, so let's find that derivative. Now we want to find the values for the intercepts that give me the smallest value of L. So what I'm going to do is I'm going to derive L with respect to the two intercepts. I'm going to derive with respect to beta naught, and I'm going to derive with respect to beta 1. I normally try to skip all these derivations, but this one's a little bit important because it does require us to think a little bit. We can't just plug numbers and call it a day. So what is that derivative? I'm not going to force you to derive. I'm sure that all of you know how to derive it. That derivative would be -2 times the sum of y minus beta naught minus beta 1 x. And of course, this would be from I equals 1 to the number of observations. Because I want to find the smallest value, I got to set this equal to 0. The derivative of L with respect to beta 1 is going to be, once again, -2 times the sum of I equals 1 to n of my observation minus my intercept minus my slope times the independent variable times the independent variable. And of course, I want to set this equal to 0. In both cases, I would like the beta naught and beta 1 values that produce the smallest possible value of L. So if we have two equations here, and we have two unknowns, beta naught and beta 1. Combining these two equations and solving for the two unknowns, we will get that beta naught is going to be equal to y bar minus beta 1 x bar. Y bar, remember, is the sum of all of your y values divided by the number of observations. X bar is the sum of all your x values by the number of observations. That's a really nice equation. Of course, it's not going to look so nice for beta 1. For the case of beta 1, it will be equal to the sum, and all these sums are going to be from I equals 1 all the way to n. So beta 1 will be equal to the sum of the product of y and x minus the sum of all my y values times the sum of all of my x values. So we have the sum of the product minus the product of the sums, and this divided over n. All that divided by the sum of all my x values squared minus the sum of all my x values squared, parentheses matters here, divided by the total number of observations. We have a kind of nasty equation here, but we can get this equation by simply solving this system of algebraic equations. It's a very, very nice linear system here. All right, we've solved these two equations. We get our values for beta naught and beta 1. However, remember, we can never really truly find the real value of beta naught and beta 1, right? Because to find a true value, we will need to have all the possible collections of data points for the population. So these aren't the true values of beta naught and beta 1. These are actually going to be the estimators of beta naught and beta 1. And we call these regression coefficient estimators. Okay? So if these are the regression coefficient estimators, then my expected value or mean, we already said that the mean was, or that the value was going to be equal to the mean plus some deviation, and the mean was going to be equal to some linear equation. Well, that mean or expected value is going to be a linear equation with the regression coefficient estimator for the intercept and the regression, beta 1, and the regression coefficient estimator for the slope times your independent variable. And finally, the real value, which is what was measured, what was recorded, is going to be equal to your estimated mean plus the difference between that estimated mean and the real value, which we're going to call the residual. We've covered a lot. We've talked a lot about different equations, but the main gist of it is that if you have enough data for x and y, then you can estimate the regression coefficients, and then you can use that to estimate the mean, and then you can use that mean to estimate the true value or as a function of the residual. The general procedure will be to find the estimate for the mean and then use that estimate of the mean to determine the residual. How do we know if our fit is good or not? We're going to talk about that later. But one nice way to know if your fit is good or not is to make sure the residual is minimized. It will not always be zero. In most cases, it won't be zero. But at least try to make sure that it is minimized to give your model some sense of validity. So we have a lot of equations here. I would like to simplify them a little bit. However, in order to simplify them, I'm going to define two statistics. These are only defined as a way to simplify our calculations. So don't worry too much about understanding what they mean. They're just there to simplify our calculations. I would like to define a statistic called the sum of errors of x, of the product of x with x. And that's essentially going to be the sum of each individual value of x minus the mean of x squared. That's it. So the sum of squares of x with respect to x. And if we solve this, this sum, we will end up with the sum of x squared minus the sum of x squared divided by n. The parenthesis matters. It matters a lot here. I'm also going to define a statistic called the sum of errors of the product of x and y. That's going to be defined as the sum of the difference between x and its mean times the difference between y and its mean. Now, a couple of things you want to note. First off, this value is always going to be positive because it's squared. However, that doesn't really imply that this value will be positive. Right? We could have the situation of one of these terms being positive, the other being negative. So this sum naturally may be smaller than this one. Who knows? But we may expect it to be smaller. Okay. It's not really a general rule, but just something you may want to observe whenever it is you are using this to calculate data. Rearranging this, solving for the sum, this gives me the sum of the product of x and y minus the product of the sums of x and y divided by n. So the reason I define these statistics to simplify my calculations is that this form, right, these two are going to show up a lot in regression analysis in different equations. So in order to prevent you from having to calculate and recalculate them, we just assign them to a statistic, and then we can just use this value to solve our work a little bit faster. As an example, we saw in the previous slide, in the previous piece of paper, that beta 1 was going to be equal to all of this divided by all of this. So we can write it a little bit simpler as s of xy divided by s of xx. To review the rest of our equations, beta naught, the estimate of the intercept, can be found as a function of beta 1, the estimate of the slope, x bar. And finally, our regression equation is going to be the estimate of the mean, y bar equals beta naught plus beta 1 x. Wording is very important here. Notice that I'm not calling this the estimate of the value or the estimate of y. This is actually the estimate of the mean of y. And this is something we want to keep in mind. When we apply regression analysis, we're not really trying to solve for the true value or the observation. We're actually trying to solve for the mean of the observations. So hopefully that will be something that you can keep in mind, especially as you apply regression analysis in your careers. I mentioned that you should have a laptop ready, and I uploaded a spreadsheet called Table 11.1 on D2L. I would like to now work on a group problem, an in-class problem, not group, and an in-class problem with you. To follow along, make sure that your equations are there and that you're correct. Don't just type in the answers, actually try to calculate them yourselves. So let me switch to my computer so that we can work on the in-class problem for today. And don't worry about uploading it until after class. I'll give you some time after class to upload it. So this is table 11.1 from your textbook. This table gives us the hydrocarbon levels as compared to oxygen purity. For simplicity, I have set my hydrocarbon levels to be my X or independent variable. And I have set my oxygen purity to be my Y or dependent variable. The purpose of collecting and tabulating these data is to determine if the hydrocarbon level in water does in fact affect the oxygen purity level, and how. Okay. So what I would like to do now is to come up with some relationship, perhaps a linear relationship, that can allow us to plot an estimate of the mean of these values. I'm going to start by plotting this. I know we've already seen the plot from the textbook, but it would be nice to see just visually how this looks like before we start working on it. So I'm going to do a nice little scatter plot here. Looks kind of ugly. Maybe we can modify this a little bit. This looks a little bit better, but it could be better. Let's plot from 80 to 100. Yeah, 85 is fine. There we go. So now we have this nice little plot of our data. We've already seen the data before, and I think Jaden, your classmate, had mentioned that the data looks like it could be linear. Right, so this data looks like it could be linear, and let's see if it actually is. We'll figure this out by trying to fit a line to the mean of this data. All right, so if we can in fact fit a line into the mean of this data, then yes, it will in fact support our assumption that it does follow, that the mean does follow a linear relationship. So let's get to work. I have some of the equations here. I know that you have them on your notes, but I'm going to try to go as smooth as I can in terms of solving this problem, but I will need your participation to let me know when we can or can't move on, okay? So let's start. In general, right, what I'm trying to solve, right, the end goal of this exercise is to come up with some relationship for the mean. In other words, we're trying to figure out this equation for the estimate of the mean as a function of the independent variable. But of course, to find this equation, we need to find our two regression coefficient estimators. So because we have to find these two regression coefficient estimators, we're going to have to come up with a couple of additional equations. We already know that the regression coefficient intercept estimator is a function of the slope estimator. So we can come up with the equation for the slope estimator. And of course, we have these two statistics, which just help us to simplify our data. It looks like right now we have more or less what we need to solve this problem, to come up with a nice regression equation, a nice linear regression equation for these data. We need a bit, right? For example, we can see that my intercept estimator is a function of y bar and x bar, where y bar and x bar are simply the means of x and the means of y respectively. So let's find them. Let's find y bar and let's find x bar. I'm going to start with x bar. So I know that the mean of x is the sum of all my x values divided by the number of observations. So I am going to start by adding up all of the values in my independent variable. So I have a sum of about 23.92. For your submission, obviously you don't have these nice little equations typed down, but you don't have to type them down. Just make sure that you identify everything it is that you're solving. So in this case, I can just say this is the sum of x. Okay, and we have the equation here in case you don't remember what it is we solved. Okay, so we have the sum of x. Now I would like to determine, and let me just add a little column here so it's a little bit more clear. I would like to determine the mean of x. Right? I want to know what the mean of x is. Of course, the mean of x is simply equal to the sum of all of my x values divided by the total number of observations. So what is that mean of x? I have my sum of x. I have my observations. What I can do now is take that sum and divide it by the number of observations. That's one way to solve for the mean of x. Perhaps another way is to count the number of observations first. Then take the sum of x. I'm just solving the same thing. I'm just using a different method and dividing by that count. Same thing. A third way that you can get the mean of x, which would be the simplest way, is to use the average function in Excel. Take the average function, select your data, and it's rounded up. Let me add more decimal points. And there we go. We have the same value for the mean of x. So there's many different ways that you can calculate the mean of x. I don't think that warrants any additional explanation. So let's move forward. We can now calculate the mean of y, and we can follow the same procedure. I'm going to show all three. First, we can add up all of my values in my y variable. And then to get my mean, all I would have to do is divide those values by the total number of observations. I could also just take the sum and divide it by my count variable, which I already had set up. Or if I'm feeling a little bit lazy, then I can use the average function. In all these cases, we will get the same result. All right. Up to this point, are there any questions? No, that's good. That's what I thought. It looks like for now we've been working on things that we seem to know. Okay, good. So let's start adding some additional things. We are going to want to calculate these statistics. And in order to calculate these statistics, we will need to know what the sum of all my x values squared is. So an easy way to do that would be to just create a column. And in this column, write down all my x values squared. Let's make it look a little bit nicer here. All my x values squared. All right. So in this column, I'm going to take all my x values, and I'm going to take all my x values, and I'm going to square them. And of course, the sum of all my x values squared will be just the sum of everything in that column. So far, nothing too complicated. It looks like we still know what it is we're doing. Let me move these a little bit so that we don't lose these equations. But so far, it seems like we're on the right track. In order to calculate my first sample statistic, SXX, which is the sum of squares of the errors in the product of x, all we have to do is take the sum of x squared minus the sum of x squared. The parenthesis matters here. Here I'm saying minus this sum squared. And just to be safe, I'll add some parentheses here. Divided by the number of observations. So I get a statistic, a sum squared errors of 0.68088. Okay, so I got my first statistic, the sum of squares in x. And the sum of the product of x and y will be my second statistic. This one a little bit more complicated. In order to get it, you can see that we need to find the sum of the product of x and y. So of course, this forces me to create yet another new column for the sum of the products of x and y. So this is the product of x and y. This will be equal to x times y. The sum of the products of x and y is simply here. Oh. There's a question in the chat. I cannot hear anything. Can other students hear? If not, it could be a problem with my microphone. Okay, so it looks like other students can hear me. I just realized if I ask that and nobody can hear me, nobody was going to answer. So next time I can also ask that question in the chat. Let me just write in the chat for Jaden. And it looks like he is going to connect. So let's try to take it a little bit slow here. And in the meantime, while Jaden reconnects, are there any questions so far? Okay, no questions yet. That's fine.
Sorry,
no
can you show SXX again?
Yeah, here's the equation, right? It's the sum of x squared, which we already calculated here, minus the sum of x, which we already calculated here, but squared, so this number you have to square it, divided by n. And n is the number of observations, which I have here. Okay?
Okay, thank you.
No problem. And while we wait for Jaden, let me just write down some additional terms here, just descriptions, so that since you don't have my nicely formatted equations, you could still show your results without having to write all these down. Just make sure you explain what each of your values is, what each of your values are. All right. All right, Jaden is back. For the sake of Jaden's reputation, I'm not going to read the reason why his audio didn't work so that future generations who watch this video don't laugh at him. All right, so let's move on. We want to calculate our next statistic, the sum of the errors of the product of x and y. And we can see from here that it is the sum of the product of x and y minus the sum of y times the sum of x divided by the number of observations. So let's calculate that. We have the sum of the product of x and y, so we already have that sum here, minus the sum of all my y values, I have that here, times the sum of all my x values, divided by the number of observations, gives me about 10.17. All right? So remember I mentioned that we would expect this to be lower, but not always, right? So even though this may have negative values at some point, right? We can see that it's not always lower. And the reason this occurs is because here we are considering also our y variable, which is significantly greater than our x variable. Because the variable is significantly greater, then the deviations from the mean are going to be greater as well. So like I said, it's a general trend, but we shouldn't use it to draw conclusions. So we have all of our statistics. Notice that we have all the statistics we need to now solve our for our regression equation. At this point, I would assume that there are no questions, but let's see, we have another question. Can we repeat the step for Sxy? We have the equation here. We have the sum of the product of x and y. We've already calculated that, right? The sum of the product of x and y. Minus, we have the sum of y. We already calculated that here. The sum of x, we calculated that here. Divided by n, and n is here. Now remember, this is simply the sum of x and y, right? This is one term minus, and this is another term. So when I write down my equation, I do have my first term minus, and then my second term would be sum of x times sum of y divided by my n value. All right, let me know when I can continue. All right, seems like in general students are ready to go. So let's continue. And now let's compute our coefficient. Brian is very excited to move forward in this class. That's good, that's good. Caps lock shows excitement. All right, so let's find our coefficients. I'm gonna start first by finding the slope estimator. The reason I want to find a slope estimator first is because we don't really have it as a function of anything else other than our two sum statistics. So slope estimator is equal to Sx of y, so S sub xy, times S sub xx, or divided by S sub xx. We have a nice slope of 14.9 for almost 15. That's a nice little slope. Let me just write this down here. And now we can calculate our intercept coefficient, beta naught. Remember, these are estimators of the coefficients. They are not the coefficients themselves. So while you're wrapping up your previous calculation, I'll just add a little label here and format it a little bit. From the equation, we can see that that coefficient is equal to y bar, and y bar is the average value of y, minus beta 1, and again, this is the estimator of beta 1, times x bar, the average value of x. So we get a nice intercept coefficient of 74.2. So finally, what our equation will look like is beta naught, so 74.2 or 3, plus beta 1, 14.9, times x. That is going to be our equation for the estimate of the mean. I'm not going to expect you to write down with these nice fancy Greek letters. You don't have a Greek keyboard, although I do, but you don't. So instead, what I'm going to ask you to do, instead of writing down the equation, what I would like for you to do is calculate that estimated mean for, well, for your data. In other words, I would like to calculate this little y hat. I don't know how to draw a hat. Let me see. No, it doesn't let me draw a hat. Yeah, not for y. I like to calculate this little y hat. We have in the chat the Windows key plus the period mark brings that stuff pretty easily. That's very, very, very good. And beta 1. Let's go back to the equation of beta 1. We have a question in the chat about beta 1. The equation for beta 1. Beta 1 is going to be equal to your sum of the error of the product, so S of xy, which we already calculated here, divided by S of xx, which we've already calculated here. So the reason we do these two calculations first is so that we're not plugging in all of this into this equation. And because we're going to see these later, they're going to be very, very useful for calculating other things. So it's easier to just calculate them now so that we can just refer back to them when necessary. All right, so what I would like for you to do now is to determine what my values of the estimated mean for everything, right? For all of my data points. You actually don't have to do this because it's a linear equation. Technically, you could just find values for 2 points. However, just for this submission, try to write down the values for all the points, not just 2 points. So I write down my equation. I have beta naught. Remember, this is going to be a fixed variable, so press F4 to fix it, plus beta 1 times x. And this gives me the expected mean. Okay. Finally, how do we know if our data actually is correct? The good thing about using Excel is that Excel does all of this automatically. So we can use the different, we can use Excel to determine if our regression fit is in fact correct or if it isn't. What I would recommend to do, so could we go through y hat again? Sure. Y hat is this equation. So it would be the estimator for the intercept plus the estimator for the slope times each x value. So for each different x value, you have a different y hat. Remember, these two variables don't change, so you're going to have to fix them in Excel. Bailey says that the first 2 rows populated, but everything else popped up as zeros, probably because you did not fix them yet. Remember to fix your cells, and you fix your cells by pressing F4 or function F4 on your laptops on them. Okay. I would recommend, however, that you look up the general intricacies of Excel on your own, because really my goal is to teach you the statistics part, not necessarily the Excel part, okay? But for now, as long as you can get one value done, then you can figure out how to get the rest, the others, okay? And don't worry, I'm going to give more time after class ends for you to submit the in-class problem. It won't be due exactly at 5. So you have a little bit more time to fix it, make it look nicer, because I want to grade this. I want to make sure it looks okay. All right. So how do we know if this data actually looks good or doesn't look good? What I'm going to do is I have this little plot here that we've already plotted, and I would like to compare our graph, our equation, to the equation that Excel would actually show. Renee is already a little bit advanced and notes on the chat that we can look at the R-squared value. We will look at the R-squared value. But for now, just to do a general check, first let's try to fit a line into this curve. Double click on the graph, chart element, trend line, and let's fit a linear equation. We have this nice little line here, and we would like to know if this line actually conforms to our y-bar values. 2 ways to do that. One way is to double click on the line and show the equation. And we see that this equation has a slope of 14.947. And notice that our slope is 14.947 and an intercept of 74.283. And our intercept is also 74.283. So it looks like we did a good job. If you're more of a visual person, such as myself, one way that you could prove this visually is by adding a data set where you will plot your y-hat values to your x values. And if this is correct, then that data set that you plot will be exactly at the line. Notice that it follows your line exactly. For your submission, I don't really want to see this trend line for your submission. So I don't want to see this equation here, and I don't want to see this trend line here. Instead, I would like you to plot the trend line manually based on the data that you calculated. This looks a little bit disorganized, so I would recommend you plot it as a straight line rather than as what do you call them, as points. And I'm going to have to fix this a little bit. Ooh, this is not good. I'm gonna have to fix this by arranging these in ascending order so that this doesn't look like a really, really messed up line. So that's something that you're gonna wanna keep in mind when you prepare your submission. Relatively simple fix. Just grab all these and sort them in ascending order. And let me delete this data set from the table. I'm going to copy them here so I don't miss out on my data. All I'm doing now is copying my X and Y values and just putting them in order. To sort them, just select both. Make sure that the X values are on your left and just click sort and filter from smallest to largest. And now I should be able to plot this or add this to the graph. Oh, this did not work. What did I do incorrectly? Oh, never mind. As long as you have this table, we should be fine. I will need to look into what I did. Oh, I missed one point. Thank you. Ah, I see. Thank you for that help. Huh. Now it looks like I'm still not. Oh, I see. Now I see what my problem is from thing. It's all right. So my problem is that I have two different x-axes, so I don't have them organized correctly, but that's fine. I think in general, as long as you can plot your x bar and your y bar, even if it's not a line, it's okay. But as long as you can plot it, so we can actually see that linear trend, for example, by plotting this, by plotting your y hat values here, that should be fine. Now remember, you don't actually have to write down the equation for me to see it, but you will have to at least calculate your y hat values. So as long as I have everything I need here, right? And as long as I have all of my calculations here, such as my statistics, then you should be good for your in-class problem. Now, I know that at this point, all of you may be thinking, well, what's the point of doing all these calculations, right? If Excel just does it automatically in a second. Okay. Oh, we have some nice recommendations in the chat to get it to look like a nice little line. Kind of curious because I did get it to look kind of nicer on the last on my last semester. I was probably doing something different, but it's okay. We'll figure this out. Let's see. I don't know why it's doing for one thing instead of the entire data set. Let me see.
You have to keep them all selected. There we go.
There we go.
You're missing a couple.
Is it all? Yeah, it's not selecting all. Let me see if I can just, from the table, just select the entire series. I think that should have selected all of them, but I'm not sure. There we go. And let me get rid of the marker. There we go. There we go. Thank you. So this is kind of what I want to see, right? I want to make sure that you have this calculated. I want to make sure that you have all these statistics calculated. And that is the general procedure for a linear regression. Like I mentioned, it's a pretty straightforward procedure, right? You calculate several statistics from your data, and then you use those statistics to estimate your regression coefficients. A relatively straightforward procedure, and as long as you follow the steps, you should be able to get it done correctly. Now, in this case, we are assuming, right, that this line does in fact represent the data very well. However, we are going to have to look into different methods and techniques that we can use to see if the data actually does agree with your line. Now, Renee has mentioned R-squared probably twice over the past two classes, but we're not going to talk about that just yet. Instead, what I want to talk about is where it comes from, or how we can calculate the values that we need to determine our R-squared term. Now, if you hear the word R-squared and you haven't really heard this before, it's okay. It's a really common statistic value, but we will talk about it and we will learn about what it means a little bit later in today's class. So let's go back to our camera here. So we've solved this first in-class problem. Don't submit it just yet. I don't have a Dropbox for it yet. And also there's still some parts that we haven't completed. We have our first in-class problem. I mentioned that as long as we know where the mean is, or as long as we can estimate where the mean is, we could try to find the real value by estimating the variance. Now, of course, we don't know the real variance of our population. What we could do instead is to estimate the variance using our sample data. So in order to estimate my variance, let me first define the error sum of squares. A nice, really useful statistic for regression analyses. We define the error sum of squares as simply the sum of all the squares of the residual. Remember that the residual was simply the difference between your estimated mean and your actual observation. Error sum of squares is a really nice statistic, again, very useful. As you can see, if the error sum of squares is smaller, then at least that allows you to conclude that your line is a better fit for that data that you collected, not for the whole population, but for the data that you collected. We could use this error sum of squares to estimate the variance. The variance estimator is going to be equal to the error sum of squares divided by n minus 2. Remember, we divided the sample variance by n minus 1 to make some corrections. Now we divide by n minus 2 to make some additional corrections on how the error sum of squares may relate to the true variance of a population. So these are two additional statistics that we're going to want to keep in mind: the error sum of squares and the variance estimator. I'd like to define the total sum of squares as the sum of the squares of the difference between your observed values and the mean of those observed values. So the error sum of squares is the difference between your observed values and how you estimated the mean of those values. The total sum of squares would be the difference, the sum of the square of the difference between the real values or the observed values and the average or mean of those values. Of course, we can expand this a little bit to land at the sum of y squared minus n times y bar squared. That's my total sum of squares. Error sum of squares and total sum of squares are very, very, very important statistics. They allow us to see how our data is dispersed. For example, in the case of the total sum of squares, has nothing to do with your model. Instead, it gives me an idea of how far away the data is from its mean. Error sum of squares then gives you an idea of how far away the data is from your estimated mean. This definition of the total sum of squares allows us to relate the two. Because notice that based on this definition of the total sum of squares, and based on this definition of the error sum of squares, we could do a nice rearranging to calculate the error sum of squares as a function of the total sum of squares and my regression coefficient estimators. This may be a nice, useful function for you to have because it's a little bit harder to compute this. This will require us to compute an additional variable y squared, and just to save us the trouble, we might as well just calculate the error sum of squares and then use it to determine the total sum of squares. So just solve here for total sum of squares. Of course, you can calculate it however you want. And finally, we go to the residual coefficient. Now, your classmate Renee has been talking about an R-squared value for the past couple of days. Now we are going to finally introduce that R-squared value. The residual coefficient, or R-squared, is defined as 1 minus the ratio of the error sum of squares to the total sum of squares. And what does this tell me? Well, we can think of it this way. The smaller the error sum of squares is, the smaller this value, the closer R squared is to 1. Now, ideally, we define a good, and I want to use quotes here, a good model as one that minimizes the error sum of squares. So what we're looking at is the smaller this error sum of squares is, right, then the bigger R squared is, the closer to 1 it will be, and therefore the better the model will be. Why do we need a ratio? Because this ratio ensures that R squared as a value remains between 0 and 1. And that's why we have this ratio, because the largest possible value of the error sum of squares will be the total sum of squares. It cannot be greater than that, right? The error sum of squares corresponds to your line that's like this. The total sum of squares corresponds to a mean that's just a horizontal line. And so the largest possible value for error sum of squares would be a horizontal line. If you keep moving, you'll just make the error sum of squares a little bit smaller and smaller. So it doesn't really matter, right? Anyway, this residual coefficient, again, another really important statistic for our work. Let's go back to our in-class problem and let's relatively briefly try to calculate the error sum of squares, the total sum of squares, the variance estimator, and the residual coefficient. Now, in the interest of time, I am a little bit short on time because I started the class late today. So I'm going to try to perhaps maybe speed up through these numbers just a little bit. I'd like to start by determining the error sum of squares. So SS sub E, or simply error sum of squares. We mentioned that the error sum of squares was the sum of the difference between your observed values and your estimated mean. So what I'm going to have to do here is create a column where I can find, or I can type in the difference between observed values, y, and the estimated mean, y hat, and of course, square them. So how do we do that? Not too complicated. We have our y values, purity. We want to subtract from that our estimated mean y hat values. Oops. And then we want to square these. My error sum of squares is just going to be the sum of all of these values. So we have an error sum of squares of 21.25. I would now like to calculate the total sum of squares. Again, you have the equations on your notes, so I'm not going to type in the equations here in Excel. But the total sum of squares can be calculated as a function of the error sum of squares, the estimator for the slope, and the statistic for the sum of the error of the product of x and y. So taking my equation and solving for total sum of squares, I will get a total sum of squares equal to the error sum of squares plus my estimator for the slope times the s sub x, y. So I have a total sum of squares of 173.3. We now go to calculate our variance estimator. Variance estimator should have a hat on, but I don't have my, I don't have a little hat feature here. That's going to be equal to, and let me write down variance estimator. That's going to be equal to my error sum of squares divided by n minus 2. And finally, we go to our residual coefficient. And following the equation, the residual coefficient is 1 minus the ratio of the error sum of squares to the total sum of squares. So we get a residual coefficient of 0.877. Now, assuming that all these calculations are correct, there could be mistakes, then we should have a correct residual coefficient. How do you know if it's correct? One way you can try to check it is, once again in Excel, if you do add a linear trend line, then you can make sure that you select, or that you show, the R squared value. And notice that the R squared value is 8.774, and the R squared value that we calculated is also 8.774, which means that our calculations are correct. So in addition to the work that you've done so far, I'd like for you to add some calculations for the error sum of squares, the total sum of squares, the variance estimator, and the residual coefficient. And you have your equations from your notes. It looks like somebody's getting a different value for the error sum of squares. So let's go over that again. the error sum of squares is the sum of the difference between your y values and your y hat values squared. So what I did was take or create a column where I have my y value minus my y hat value, and all of that I square it. If all these numbers in this column are the same as yours, then you should ideally, in theory, get the same error sum of squares by simply adding up all the values in this column. So you can go back and revise. Let's see, the error sum of squares is y minus y hat squared. The total sum of squares is y minus y bar squared. Those are two different values. Remember, what we're doing here is we're just subtracting for the error sum of squares, y minus y hat. For the total sum of squares is y minus y bar, which is only one value. So if we were to create another graph, another column for, and you don't have to do this for your submission, y minus y bar, oops. Let me get this parentheses down to the correct place. So if we were to create this column, we'd have our y values minus our y bar values. Make sure you fix that in Excel. Square it. And add those values. We would get the same total sum of squares as you can see here. So yeah, there's a difference between error sum of squares and total sum of squares. Okay. All right, so add these, follow the equations from your notes so you can add these calculations to your group problem. I mean, to your in-class problem. I keep saying group, to your in-class problem. Now we're going to talk a little bit more about the significance of R squared and about how we can use R squared to determine the validity or invalidity of a model. So don't worry too much about it now. Right now, I don't want you to draw any conclusions about whether this fit is good or not for the model. We're going to work on that. We're going to work on that in a little bit. Right now, we decided to plot a linear relationship based solely on Jaden's word. So Jaden said it looks linear, so we decided to plot a linear relationship. That's a bit of a lie. I did not model this class based on what Jaden said. It was going to be a linear relationship anyway. However, realistically speaking, sometimes, right, sometimes you don't have linear relationships in physical, when you're studying physical properties, physical relationships. Sometimes our relationship is simply not linear. And when that happens, when our relationship is not linear, then we have to ask the question, what do we do? Well, if our relationship, our physical relationship is not linear, then perhaps we are going to have to find a non-linear regression model for our data. For example, think of your height as a function of your age. Of course, as you get older, at least for the first 25 years of your life, you get taller, maybe even less than 25. However, the rate at which you get taller is different, right? There's a difference in height between, say, a 4-year-old and a 10-year-old than there is between a 24-year-old and a 30-year-old. The difference is actually not the same, which means that if we were to plot a graph of your height based on your age, that graph will probably not look linear. In fact, and this is me just guessing, not really using data, I would say that that graph would look something like this. Now that's my estimate, right, of what a graph of your height with respect to your age will look like. Okay? So this relationship is not linear. which means if we would like to find some sort of empirical regression equation to fit into this data, into these data, then it cannot be a linear equation. Now, I want to take the cop-out version and say, well, this is not really the focus of this class. It's outside of the bounds of this class. So, all right, good luck figuring that out. However, here's the thing. In some situations, it's possible to take your data and transform it. You transform it by adding some function to it, right? And you can transform it so that it can be expressed as a straight line. Now, when this happens, the models that transform data so that they can look like a straight line are called intrinsically linear. So what do I mean when I say this? Well, the most basic example of this comes from my fluid mechanics lab course. Now, some of you have already taken my lab course, others are taking it right now, but one of the things within my lab course is that sometimes our relationships, our fluid relationships are not linear. So for example, there is one experiment where students collected data, and I'm going to simplify this because this is not really a fluids class, so I'm just going to simplify a lot. But in one experiment, students collected data that should have followed a power relationship. The equation is actually a little bit more complicated, but essentially looks something like this, right? Where they had to plot this value, which is the independent, dependent variable. K here is a constant, some constant that we don't know, and Q is an independent variable. I noticed a typo in the notes. I mixed independent and dependent in the explanation of this example. So we want to plot this data and we want to try to find an estimate for the value of K. And you can do this, I would say, by plotting the data and then fitting a curve and using that curve to find the constant for K. However, Excel doesn't really do this, at least not automatically. It does, but not automatically. Excel instead gives you a polynomial curve. So instead of giving you a curve of the form y equals constant x squared, it'll give you a curve of the form y equals ax squared plus bx plus c. So students obviously get a little bit confused. They don't know what to do. This, I'd say, is the simplest example of showing an intrinsically linear relationship, right? What you can do instead is to create a variable, I'm going to call it x, where that variable equals q squared. And then I am going to plot c versus x. So if I plot c versus x, knowing that c equals k times q squared and x equals q squared, what would that plot look like? If I plot c versus x, a straight line, that's correct. My plot would look essentially like a straight line. In fact, you can see here, if I replace q squared with x, my equation becomes a nice linear equation. So what I can do is plot my data, fit in a linear regression curve using the method that we already practiced, and then back calculate, right? Replace your x with q squared, and then you'll have your equation, right? Think of it this way, right? You plot your data, you fit your regression curve, you get your nice little linear equation for your regression, and then you just replace your variable with q squared, and you're done. You have a nice power equation, a power regression equation that you came up with using the linear regression equation methodology. So earlier in this class, I mentioned that sometimes we underestimate how powerful linear regression is, and I think this is one of the ways we can underestimate it. A lot of physical properties with the proper transformation can become intrinsically linear, which means that we can use linear regression as a method for a lot, maybe not all, but I would say a significant portion of physical properties that we want to model. So that's when we say we transform a variable, essentially we add a function to it in order to turn it into some other variable that looks linear. The most common transformation, I would say, in the natural sciences is the log-log transform. The log-log transform essentially tells me that if I have a graph that is not linear and I transform it by taking the logarithm of those values or by plotting them in a log-log scale, then I can make that graph look somewhat linear. The log-log transform is a really, I would say, beautiful transformation because it allows us to understand concepts from biology, concepts from physics, concepts from a lot of different fields in the natural sciences that would otherwise have not been very understandable. Okay, so if you ever do research in the biological sciences or natural sciences, you may encounter the log-log transformation several times, many times. So I would like to just show you an example. We're not really going to work through an example, but I did want to show you an example related to some of my research. So you can see how helpful this log-log transformation is. And let me just search for it here. All right. All right, so this is some information that I'm putting together for my doctoral studies. I don't have to go into the details of what this information relates to, although you can read. And this is the plot of my data. As you can see, not a very nice plot. I have a power law here fit into it, but we can get rid of this power law equation for now. This is my plot. That is my plot. Okay. Is this linear right now? Do you see some sort of linear relationship here? It most certainly does not look linear, right? The fact that we have this huge different in points, which are actually not outliers, you'll notice that these are not outliers. But if I were just to look at this graph on the basis of this graph, I would assume that these are outliers. But I can still try to look at the graph a little bit more closely. So perhaps I can plot my graph, I would say a nice little closer range. Let me plot it from 0 to, let's say, 200. Here we have my data set. It kind of looks like it wants to be or could be linear, but I'm not really sure because we have this point here. Again, it's not an outlier. If I were to just take this graph and see it without any context, I would think that this point is an outlier, but it actually is not, okay? So I look at this, it looks like it could fit some linear relationship, maybe not. Let me plot this graph all the way up to, let's say 60. And here the linear relationship starts to become a little bit less and less evident. Let me change my vertical bound so you can see it a little bit better. All right, does this relationship look linear to you? Just looking at this graph, does this look like a line could be fit into it? Not really, right? That's correct. So again, not a very linear relationship. I can keep zooming in, right? I can keep zooming in to see if I can identify some trend, but it looks like the general trend is, it looks like the data is just scattered all the way throughout, and then there's a lot of data cluttered at the corner. That's what the trend looks like. So what I'm going to do instead is plot this data, which is what I did, in log-log scale. In log-log scale, what I'm doing is, it's still the same data, the values have not changed, but my axes have changed. So that instead of showing my axes in ascending order from 1, 2, 3, you know, in a nice little uniform distance between axes, I'm plotting them in log scale, which means that every equal distance visually in the graph is going to equal a change in order of magnitude. So from 0.01 to 0.1 to 1 to 10 to 100, 1,000, 10,000, 100,000. I do the same thing for my y-axis. Notice that every interval is an increase in order of magnitude. And now doing this, I actually have a nice, very nice, almost linear looking data set. Maybe not exactly entirely linear, but even without this line here as a guide, you can still more or less see a trend. If you ignore this last file, you can still more or less see a linear trend, at least in part of the data. I could even calculate my R-squared term. You can see R-squared is about 0.62, so maybe not as good as the one that we mentioned in the example, but actually good enough for a natural or biological thing, right? Where there's a lot of variation. In biology, there's a lot of variation. So being able to at least come up with a nice relationship is actually very helpful in the biological sciences. You can do the log-log scale this way, and you can also do it by, instead of changing the axes, you can plot the data by applying a transformation, which is to take the logarithm of each data point. And then it'll look like this as well. That's the general idea behind transformations. Now in this class, we're actually not going to go into details regarding these coordinate or variable transformations, these parameter transformations. However, I do want you to at least keep it in mind that the linear regression equation, at least the linear regression equation method that we've practiced today in class, is a very powerful method, right? It helps us to come up with relationships that otherwise we probably would not have been able to come up with. So linear regression method, very powerful method. It's not the best for every single scenario, but as long as you can apply the proper transformations, it will be a helpful method for you. Let's move now to module 15. Today we're covering 2 modules. So we've introduced linear regression equations and linear regression models. Now I'd like to talk a bit about how we can assess these models. So how we can try to study them and assess them to ensure that they are actually good fits for our data. Typically, using a regression model requires 3 assumptions. The first assumption is that the errors are uncorrelated random variables. So if our assumption, if our linear model is correct, then the errors should be almost randomly scattered. In other words, if you were to plot the error, the residual, it should be just a nice scatter with no clear trend. For example, if I were to plot or try to come up with a linear regression equation into a data set that kind of looks like an exponential equation, then how do we know that that assumption is incorrect? Well, obviously visually we can see it, but also we can see that the errors kind of like increase, then decrease, then increase, and perhaps with a little bit of math, you can actually find a relationship between your x value and your error. And if that's the case, if you can find that relationship, if the errors are not random, then your regression analysis or your choice of your regression model is incorrect. We also assume that the errors are distributed normally. In other words, if you plot your x variable and you plot the amount of errors that you get, then you should get a normal distribution, or the probability of getting errors, you get a normal distribution. And that normal distribution should have a mean of 0 and a constant variance, which means that on average, all of your errors should tend towards 0. So they should be, however much your errors are greater than 0, they should also be less than 0. For example, if you have a linear regression equation, and all your data points are above that line, then obviously all your errors are positive. So your mean of errors is not 0. But if you have points below that line as well, we should assume that if you take the mean of all of the errors, and when I say errors here, I mean dispersion. If you take the mean of all the dispersion here, that mean would eventually be 0, right? Because however many errors you have over the line is the same amount as errors you have under the line. At least that's what we expect to happen. Finally, we assume that the order of the model is correct. So that if it's a linear regression equation, that means that you're assuming that your model is linear. If it's a second order polynomial, that means that you assume that your model is a second order polynomial. If it's an exponential, you're assuming your model is exponential. Now, as statisticians, we need to conduct analyses to test the validity of these assumptions. Just because we are making these assumptions doesn't mean that they are true. We are going to have to put in some effort from our own side to try to test these assumptions and see if they are in fact true or not. So before looking into these different ways to assess whether or not a regression choice is correct or not, I'd like to talk about the normal probability plot. When you get to a point where in your career where you are selecting data, trying to fit lines and curves into that data, the normal probability plot will become a nice visual friend for you to determine the validity of your methodology. A probability plot is essentially a graph that we can use to determine if a sample data conforms or if sample data conform to some hypothesized distribution. By extension, the normal probability plot is a graph that we use to determine if sample data conform to a normal distribution. So how these plots work, typically each probability plot has its own special axis. In the case of a normal probability plot, that axis is pretty interesting axis. Let me show you some example from the book here. I think maybe page 180 something. Oh, actually a little low. Maybe page 130 something, yeah. Here we go. So this example right here shows you a normal probability plot. So you can see that the axes in a normal probability plot are changed. They're not standard. You go from 0.1 to 1, 5, 20, 50, 80, 95, 99, 99.9. Never actually reaches 100. It never actually reaches 0. And the way these axes are set up, if your sample data were to follow a normal probability, then you could plot it and it would look like a straight line. Doesn't matter the slope of it, it will look like a straight line. So that's what a normal probability plot is for. So it's a nice way to organize your axes such that when you plot your data, if it does follow a normal probability, it will look like a straight line. If it follows some other distribution, it's not going to look like a straight line. It's going to look like something else. There are different probability plots, normal probability plot, chi-square probability plot, all different probability plots, and they all have their own special sets of axes. Okay, so they all have their own special sets of axes. You can typically plot them in Excel or find online tools to plot them, but the idea is it's a nice way to visually inspect something, visually inspect your data, and maybe draw conclusions about whether it follows or not follows a plot. I don't really have a numerical way where you can just plug in some numbers and see. I mean, there are ways, but it's actually easier to just plot it into a normal probability graph and then just see just see what we have. So Renee says that the y-axis doesn't seem to follow a pattern. It does follow a pattern. So can you change the y to an anything to make it look like a straight line? I mean, you can, but then it wouldn't be a normal probability plot. So the idea behind the normal probability plot is that it follows this pattern, right? The 0.1, the next interval 1, 5, 20, 50, 80, 95, 99, and 99.9. And that pattern corresponds to the cumulative probability distribution of a normal distribution. So this axis is essentially what we call a normal probability axis. Just like we have log axes where you go from 0.1 to 1 to 10 to 100, in this way, we have to have this axis to be a normal probability plot. We can have other axes with other different patterns that correspond to different probability distributions. For example, there's a different axis for a chi-square distribution. There's a different axis for a Poisson distribution. So each distribution has its own axes. And the idea of this axis is that if the variables do follow that distribution, they should plot into a straight line. If they don't, then they won't follow a straight line. So if you take a normal distribution variable, you plot it into a chi-squared axis, it's not going to look like a straight line, and vice versa. Anyway, we actually don't cover too much into this. In fact, normal probability plots, you can pretty much do them in Excel, and they're not really a nice, they're not like a very standardized metric. Instead, they're more for visual inspection. So they provide, right? They provide visual inspection of your data, not necessarily a nice numerical value. There's actually ways to plot or try to plot a normal probability plot in a standard axis, which corresponds to standardizing your variables. You have that in your notes. It is a little bit outside of the scope of this class, so in the interest of time, I am going to skip that. But if you are interested in not having to use this and instead plotting on a normal y-axis, then there's a method that corresponds to standardizing your variables, which again, you will have them in your notes for module 15. Anyway, I present this because whenever we are trying to see if our data is correct, we could first test if our assumptions are correct. If we want to see if our regression analysis is correct, we can test if our assumptions are correct. So this idea of testing whether or not our assumptions are correct really is going to be highly dependent on the error, the amount of error that your regression equation has. Because we are studying the amount of error, this type of methodology is called residual analysis. Whereas the name implies, we calculate the residual for your linear regression, and then we analyze it. We look at it to see if it actually is correct or isn't. Remember that we define residual as simply your observations minus the expected mean from your regression equation. One way we can see if our assumptions are true is by plotting your residuals in a normal probability plot. Because if we plot our residuals in a normal probability plot and it does seem to follow a straight line, that means that the error, right, the residual, which is the error, has a normal distribution. So at least one of our assumptions are correct. Now here's the thing. Just because one assumption is correct doesn't mean that they're all correct. So we got to be careful here. We can plot our error into a normal probability plot and then see the line and see, okay, and say, okay, well, at least our assumption that the errors are normally distributed is a correct assumption. However, we can also find other ways to analyze residual plots visually. There's a nice example from your textbook, which shows different normal probability plots. I think, if I remember correctly, it should have been page 298 or 297. So let me see if I can find that. Maybe a little bit less than that. Probably I guess higher than that, 300 something. Oh, no, I was right, 290 something. Here we go. So another way, if we don't want to plot normal probability plots, another way to analyze residuals graphically is by plotting the residual versus, let's say, versus the time sequence, so in the order in which they were collected, or versus your x, your independent variable, or versus your y, your dependent variable. My recommendation is that you plot all three: residual versus time sequence, residual versus x, residual versus y hat, your expected mean variable. We have here 4 plots of residuals, and we're going to analyze them visually. We're not going to really going to throw any numbers in here. If you look at this first plot, do you see any relationship between the value of the residual and the x-axis? The x-axis can be time sequence, it can be x, or it can be y hat. It doesn't really matter right now, but do you see any relationship between the residual and the x-axis? Looks like no relation. It looks like it's not really related, right? It looks like they're just randomly scattered. So visually speaking, if you see something like this, what this tells me is that the error, the residuals, are independent variables, right? That don't really have any correlation with your data, which means that another one of your assumptions is correct. So now we have 2 assumptions that are correct. So that's good. We have two assumptions that are correct. One by looking at a normal probability plot, and one by looking at the residuals. What about this data set? Do you see a relationship between the error and the x-axis? Yep, it seems like the more you move along the x-axis, the more your error increases. This is called a funnel. And what this shows me is, for example, if this were plotted against time sequence, what this shows me is that the longer you run your experiment, the more error you get. This would also show me if it's plotted against the y hat value, then that means that the greater your value, then the worse your fit. So this actually says that the errors are correlated, they're not independent, which means that our fit is not a good fit, our assumption doesn't work. What about here? Do you notice any relationship between your x value and your errors? Just general, what observations can you make about this shape? Yep, it looks like larger errors are towards the center, which means probably that our model works better at the extremes, but it's actually not a very good estimator of the center of the value. I want to give an example of what this would look like, because this is actually very, very common. So have you ever heard of people that try to interpolate, let's say you have some data set, and let's say your data set follows a nice inverse exponential term. However, some people I've noticed, assuming that you have perhaps this data point and this data point, not knowing about the other data points, you may try to interpolate between these 2 points to find values in between. So when that happens, what essentially you have is a model that fits very, very well with your extremes, but actually doesn't fit very well with the middle values, with your average value. So it's obviously not a good model. So what this points us to is not necessarily that the errors are not independent, but this points us to the model itself not being good. So where this one kind of shows us about errors in the experimentation, this one, which is called a double bow, points us towards the model itself not being the best model. What we have here is a nonlinear relationship where you can still see some relationship between the errors and the x-axis, but that relationship moves like a nonlinear equation. What this tells me is that my selection of the order of magnitude is incorrect. So graphically speaking, we're not really calculating anything. We can more or less get an idea of how good our residual analysis is and whether or not it may be valid for our variables, for our data. I know that some of you prefer to deal with nice hard numbers. However, I would like to encourage you to sort of appreciate the power of visual methods and graphical methods. I certainly prefer the visual methods over the numerical methods, but I know that others don't prefer them because of the subjectiveness. Like, what is a straight line? Some people may think, well, this is a straight line. Well, this doesn't look like a straight line. I know there's a lot of subjectiveness. But at the very least, we can at least rule out any extremes. So if a model is very, very bad, these visual methods will allow us to rule that model out. And then later we can focus on more precise methods to determine the correct or the best model. Okay. Just like standardizing variables for a normal plot, we can also standardize our residuals and use that standardization to help our visual inspection. As a final part of our oxygen purity example, you actually won't have to add anything. I would like to just look at it a little bit visually. But as a final plot, as a final part of this in-class problem, I'd like for you to determine if your linear regression model is valid or invalid using only visual methods. I'm not going to ask about everything in the interest of time, but your book actually does have 3 types of plots here. This is for the same data set that we used. What we have here is a normal probability plot. You can see it has the same normal axes. And we have our residuals that seem to align with a straight line. So based on this normal probability plot, do you think, just based on this, do you think your regression model, your linear model is appropriate? This is residual, these are errors, and this is my normal probability axis. It looks like it is, right? It seems like it follows a straight line. So we'll say based on this that at least one of our assumptions is true. The errors are normally distributed. Good. What we have here is a plot of residuals against y bar and a plot of residuals against x. In both cases, do you think these plots point towards our model being appropriate? The idea is, does it look random or does it look like there's some sort of relationship here? It looks random, right? And if it looks random, our model is appropriate, right? Because remember, one of the assumptions we make is that the errors are independent and not correlated to each other, which means that there should be no relationship between residual and y bar or x, which means if there is a relationship, if it increases, decreases, then of course it's not appropriate. But here it kind of looks random. It looks like we can't really come up with a discernible pattern, which kind of points me towards this model, this linear regression model being appropriate. We are running out of time. We're going to go back to our R-squared discussion on Monday, and then I'd like to talk a little bit on the conceptual side about how we can use linear regression to predict future outcomes, and also how we can be wrong when using linear regression. So Monday, we're going to have a pretty heavy class. We're going to finish today's topic. I want to talk a little bit about kind of like a bonus class on applications of statistics or how to draw conclusions, and we will also review for the final exam. So I will see you on Monday, I guess online, and have a good weekend.